So we're going to be working in the land ice applications tutorial, which I hope you guys have cloned already. And in here, there's a notebook called Land Ice Applications. And that's the material I'm going to be covering. And for some reason, that's taking a minute. There we go. And I'm working in kind of a big font here. You guys don't have to do the same. Okay. So the idea here in this tutorial is to get familiar with ICESat-2 products over land ice. We're mostly going to be working with the ATLO6 product, but I'm going to give you a couple of tools for looking at ATLO3s as well. To work with this stuff, we're going to be importing sort of a general set of utilities. The only specialty modules we're going to deal with are H5Py and PyProj. And we're going to work in widget mode, which is how you get Matplotlib to let you zoom on plots. The other two magics that I'm calling here are what you need to use auto reload. So if you modify anything outside your current notebook, it will get reloaded by Python immediately. So you don't have to recompile stuff to get it to show up. So that's kind of nice if you're working with any code outside of the notebook. The things we're going to try and do in this tutorial is to get an idea of how ice sheet surfaces are represented in ATLO3 and ATLO6. We're going to look at the correspondence between ATLO6 elevations and the ATLO3 photon cloud. We're going to look at small scale features in both data products, and then we're going to look at the repeat structure of ATLO6. I'll show an example of how cross-track slopes can affect elevation differences, and we'll also take a quick look at the ATL11 product. Along the way, we're going to present a reader for ATLO3 and a reader for ATLO6. So these are things that you should be able to steal out of this notebook and use for your own purposes later on. I'm going to briefly show how to do geographic projections with PyProj. And we're going to filter ATLO6 elevations with a couple of different strategies. One of them is using the slope of the segment, and the other one is to use the built-in quality parameters. And we'll just do a couple of Matplotlib tasks along the way. I'm going to use my point collection package, which is a place where I've stored jobs that I have to do over and over again. This is available on Git, and although soon it's going to be installable using pip, it's currently just a collection of routines in a directory. And so to use it, you have to run the commands in the cells here. I guess I haven't been running the cells as we go along, so I'm just going to go back and import everything as we go. So this command should clone point collection into the directory right above your notebook. And then it should add that to the path for this notebook. So those routines should be findable. If you can run that cell, I'm going to take just a sec and look at the participants. Can you give me a no if you're having trouble with this cell? This is sort of the first place that things would go badly wrong. Or a yes if this cell worked for you. I think you'll get a collection of Git output if it's worked and nothing if it didn't work. I'm not seeing any responses at all in the participants window right now.
I'm seeing 18 yeses, Ben, and no nos.
All right, let's go with that. All right, so Tyler Satterley also put together an ATLO3 reader, which is stored in the readers directory, so we'll import that as well. I've put the data for this tutorial in the server, on the server, and under Land Ice Applications, so you should be able to get to that directly. And so I've stored the data root as a variable so that we can come back to that, with the idea that anybody who downloads this later on will be able to change that location and get the data for themselves. We're going to use the mosaic of Antarctica as a background, and then we've got ATL06 and ATL03 data. So we're going to quickly read in the mosaic of Antarctica for the region around Pine Island Glacier, which is the area we'll be working in. The mosaic of Antarctica is in polar stereographic coordinates, so I'm giving the latitude and longitude range of the data that have been downloaded, and going to make a box out of that, and then project that box using PyProj to get a set of projected coordinates for the box. And then we'll read the data in using, again, my library of routines point collection that are what I use to do this kind of task, to read in the data and then to show it. So what we do when we now have the mosaic of Antarctica stored as an object that knows where it is, and we can plot projected coordinates on top of that. So we have the Pine Island Glacier here. It's a glacier that's running from the top of the screen to the bottom of the screen, which is actually running from east to west in real coordinates. You can see the fast flowing part of the glacier is kind of right in the middle of the map. There's a lot of ice shelf down below, and the ice shelf is kind of rough, and the fast flowing part of the glacier is mostly smooth. And then we get a little bit out onto the sea ice at the bottom here. I've plotted the location for the data that we've downloaded as the blue box on top of this. So this is the area that we're going to be working in, and we'll look at different kinds of data from various locations along this plot. So now let's take a look at what ICESat-2 can do about this. So we're first going to pull in the ATL03 elevations. We're going to pick just an arbitrary track that illustrates a couple of points and read it using Tyler Setterly's script. So the way that I'm doing this, I'm specifying the repeat ground track and the cycle for the data. So we're looking at the 6th cycle of the data for repeat track 27. And I'm using the glob utility, which just takes a wildcard string and finds all the files that match it. So I'm taking the first wildcard string, the first file that matches this wildcard string. There's only one. And I'm going to read in the data using Tyler's script. And so this makes 3 dictionaries that contain the ATL03 data. This is reasonably quick. When one person is doing it all by himself, it may be a little bit slower when everybody tries to do it at once. So there are 3 dictionaries that contain the data. We're going to modify one of the dictionaries to contain the along track coordinates of the data. So I've got a script that goes into the along track that goes into the ATL03 script and creates the along track coordinates for the data points within that. And that'll give us something that we can plot. So let's just sit and wait for a second while this runs. Yeah, there we go. So now we'll have along track coordinates for each photon within the file. So now we'll select the 2L beam. So this is the left-hand beam of the center pair from ATL03. And we'll create a scatter plot of the photon data. So we're now plotting the photon elevations versus the along track coordinate. Let's do that. So what we get is a black stripe across the screen. The black stripe shows the entire band of photons that ICESat-2 telemetered down as possibly containing the surface. So ICESat-2 looks at the photons it gets back from the surface, says, oh, it looks like there's signal here, and sends back a bounded box around this, what it thinks might be the surface, with all of those photons. Now the routine that generates the ATLO3 file looks at that region of photons and identifies some of them as possibly coming from the surface. And it flags those with either low, medium, or high confidence. In this case, I'm just showing you all of the photons together. So I'm not bothering with which are low, medium, or high. I'm just calling anything that gets flagged by ATLO3 a flagged photon and coloring it green. So if we zoom in on this, let's give this a sec. You can see that there's a broad band of flagged photons. If we zoom in further, we can actually see that there's a very strong thin return coming from the surface, and then a scatter of points around it. Now all these scattered points are background photons. So those are just sunlit photons that are coming from somewhere around, that are coming from the sun and bouncing off the surface. So they're returning at completely random times. They just get distributed randomly in height, but the surface is highly clustered, so you can tell which is which to some extent. This is great, but as you saw, it took a while to load this file. And we're not actually being told where the surface is. We're just able to see with our eyes where the surface is. So ATLO6 then goes and says where the surface actually is within this plot. So in the next couple of cells, I'm going to show a very simple reader that takes apart an ATLO6 product and returns a dictionary that contains the variables you need to plot where the surface is. This is a simple script, a simple function. It takes the file name, the beam name. You can specify which fields you want to use, or you can just use the defaults. You can specify which points you want to read, or you can just read everything. And you can specify an EPSG number. So an EPSG number is a number that specifies the projection to go from latitude, longitude to projected coordinates. In our case, we're going to use an EPSG of 3031, which is a projection, the same projection that the mosaic of Antarctica is in. And there's a website that I think I've quoted below that tells you where to find an EPS. Yeah, EPSG.org will tell you what each EPSG number means. So 3413 is the one to use for Greenland in most cases. 3031 is the one for Antarctica. Again, these are just codes that specify that particular map projections. So what this track does, okay. Another thing that will be handy to possibly steal from this file is a regular expression that pulls apart an ATLO6 file name into the different pieces. So if you run this little piece of code, this compiles a regular expression, and you can then give that regular expression a file name, and it will tell you what the different parts of that file name mean. So this is going to pull apart the date, the repeat ground track, the cycle, the region, the release, and the version. And we're going to store each of those things in the dictionary that we're putting out from this reader. So the script then opens the file. It opens it as it uses H5Py to open the file. And it goes through the field dictionary. And for each beam, it pulls out the variables in land ice segments and stores them by their field name in the dictionary. So it takes the fields from the H5Py file and turns them into NumPy arrays and stores them in the dictionary. Okay, and then after it's read the variables from the file, it uses PyProj to convert those, convert the latitude and longitudes into X and Y coordinates. And it stores the information that is pulled out of the file name as the repeat, sorry, hang on. Sorry about that. I swiped when I didn't mean to swipe. Let's see where this takes us back to. All right, so this seems to have taken us back to an okay spot. So it stores the cycle and repeat ground track and beam information in the same dictionary. So again, let's go back for the same repeat track and cycle. Let's find the ATL06 file that goes along with it. We'll read in the data into a dictionary called D6, and we'll plot the elevations on top of the ATL03 data in the previous axes. So I'm just issuing more plot commands. So the ATL06 heights should turn up on top of the ATL03 heights. And let's see what that looks like. So now we have the ATL06 elevations plotted in red on top of the ATL03 elevations. And so if we move around on this plot, we can see that the ATL03 and the ATL06 are giving you sort of the same story, but now instead of diode photons, what we have are one elevation every 20 meters. And if we zoom in on this further, we can see that there are some cases where there's some sort of feature we can see in ATL03 that doesn't really show up in ATL06. But in general, ATL06 simplifies our view of what the surface looks like. All right, so I'm going to leave that right there. Now, what we've looked at so far is cycle 6 of ATL06. Actually, I'm going to stop sharing for just a sec. I want to do a quick check-in with participants. Can people give me a go slower, go faster, or just a yes here and tell me how this is looking right now? I want to do a quick survey for how the pace is and if I'm talking too fast.
Are you able to see the results, Ben?
No, I can't see I can just see a few people at once. Is there a way of seeing a summary?
At the bottom, it gives a summary next to the yes and no buttons. For me, it does, but maybe that's because I'm the host. We're getting right now 33 yeses, 1 go slower.
Okay, all right. I will go a little bit slower. Sorry about that. Okay, so hide that. So what I've shown you so far is cycle 6, which apparently happened on a pretty nice day. Cycle 5 was on a much cloudier day. So let's take a look and see what happens when all is not going well for ICESat-2. So I'm going to pretty much repeat a previous cell. We're still going to be looking at GT2R, but we're going to look at cycle 5 instead of cycle 6. And this is again, repeat track 27. So we'll find the ATL03 file, we'll find the ATL06 file, and we'll plot everything on screen. And my experience with the previous cell makes me think that this might take a couple of minutes. No, not so bad. Okay. So now we've got something that looks a lot messier. We have places where the signal finder for ATL03 didn't find the surface at all. And here we've just got nothing telemetered back. We have some cases where we have something that doesn't look like an ice sheet surface, where ATL06 is bouncing around. And we've got this green stripe across the bottom of the screen. Now the green stripe is flagged with a special set of flags, which indicates that nobody should believe that this is the surface. This is what we call the transmitter echo path arrival. And these are actually photons that were fired into an optical fiber on board the spacecraft. They rattled around this optical fiber for a while and then came back to the detectors. And we do that so that we have an idea of what the system impulse response is looking like. So we can see what signal we're transmitting, and we can see if there are any delays between channels that we need to take into account. So this is a really valuable thing for the spacecraft to do. It shows up close to the surface a couple of times every orbit. And so it turns up as sort of a diffuse band of photons that can be either below or above the surface, usually apparently below the surface. And since we know where it is, we just flag it. And so if you pull up an ATLO3 and just look at it this way, you'll see these bars every once in a while, but they are identified so that the higher level routines can ignore them. And in general, that's what you should do too. But still, this is independent of the fact that this is a cloudy return. But if we do some zooming in on this, let's zoom in on some place where things have not gone very well. Can see that in a few cases you can see the surface, but but the flagging routines didn't find it, and ATLO6 didn't find it. In other cases, we can see that we have a surface, but it's clearer than what we saw in the previous example. No, I'm just connection to wake back up. There we go. So we're getting clustered photons on the surface, but there are not a lot of photons for a lot of these segments. So ATLO6 is struggling to stay on the surface. The ATLO3 signal finding is struggling to stay on the surface. So these are cases where you would not necessarily want to believe all of these elevations, and you would not really want to calculate elevation changes from one repeat that contained one of these nice returns and a repeat track that contained one of these bad returns. So we need a strategy for ignoring the photons that aren't any good. We've got a couple of different ways of doing that. The way that's kind of built in, the way that I think works in most cases, and is kind of, in my mind, the standard way to do it, is to use the ATLO6 quality summary flag. Now, this is something that is read by default by my reader. It's in the top level group for all of the beams, so it's pretty accessible. It's, I think, the way that most people should go about deciding whether a signal is something that they should use or not. We have an alternative way of doing this, which uses the slope of the segments to make sure that each sloped segment is compatible with its neighbors. So I'm going to introduce a routine that plots the along track sloping segments for ATLO6 just as another thing that you can add to a plot, and something that evaluates how consistent each segment is with the previous and next segments. So this is an additional way of filtering segments that may be helpful. It may be nice to use in conjunction with the ATLO6 quality summary flag. So we'll try both of these things out. So let's define a function that takes one of these dictionaries that's been read in by the ATLO6 reader, and then a routine that looks at the along track slopes and decides whether a particular segment is compatible with its neighbors. And so it does this using the along track slope. So if you remember that each segment has an along track distance and a along track slope, and it overlaps with its neighbors by 50%. So we can look at each segment and find the minimum difference with adjacent segments. So this segment has a large discrepancy with the next segment in line, but it agrees pretty well with the previous segment. So for this one, we would report that it is compatible with one of its neighbors. We report the minimum difference with adjacent slopes. If this one had the same slope, but had been way high up in the atmosphere, we would see that it did not agree with either of its neighbors, and we would assign a large value to the along track difference. So here's a function called minimum segment difference that looks at the minimum difference between any segment and its neighbors and tells if it has a large difference. So we just return that difference. So let's see what each of these looks like by replotting the data. and using the scatter plot function to show where those differences are large. Okay, so in the top plot, we're showing what ATL06 quality summary shows. In the bottom plot, we're showing what the minimum segment difference function shows. So if we zoom in on this, in that problematic area we were looking at before, we can see that most of the coherent areas are flagged as being good by ATL06 quality summary. A 0 value means no problem has been found. So we can see that along here, there's a coherent area that looks like its surface elevations. Then when we get into the scattered area, most of those are flagged as bad by the ATL06 quality summary. If we look at the minimum along track difference, we can see that, again, in these areas where the data are really scattered, the difference flag comes out as something large. So we have two different ways of looking at flagging errors in the data. They both give the same answers in this case, but if you found that one of them was not working, now you have a tool that lets you look at the other one. Okay. Okay, so in the next segment, the next area, we're going to look at the repeat track structure of ATL06 data. So we're going to look at the big picture. We're going to combine data from multiple tracks around Pine Island Glacier. And we're going to look at this in the projected coordinates, which let us plot on top of the mosaic. So we're just going to find all the ATL06 files in that directory. And we're going to try and read all of them. And as people often do in Python, we're just going to use this structure where we say, try to do something, and then complain if it gives an error, but get on with your life after you've encountered that error. So we have this try and accept structure is something that you see a lot in Python code. It's a way of doing something that you think will work, throwing an error if it doesn't work, but moving on and just reporting the error and getting on with your life. So I'm complaining every time we try to read one of those files and we don't find the data that we're looking for. And that can happen because we've just downloaded a geographic area of ATL06 data. In some cases, there are no data in GT2L. And in those cases, one of the scripts throws an error. We're going to count those, but we're not going to do anything about them right now. So there are 18 errors out of this. We read 173 data files. But we now have the data in memory in a list of dictionaries. So now let's take a look at those data. Oops, I accidentally ran that cell again. Let's let it do its thing. Okay, there we go. All right, moving on. So now let's make a map. So these are the repeat tracks over Pine Island Glacier. I've split those up into cycles 1 and 2 and cycles 3 and greater, because cycles 1 and 2 were not pointed at the repeat tracks. That was the time when we were still figuring out how to steer ICESat-2 properly. And so you can see just in this zoomed out view that we have an irregular distribution of tracks. Once we get past cycle 3, we're now on the repeat ground tracks, and we're measuring every track on an exact repeat cycle. So now we have a regular pattern of tracks. If we zoom in, this is sort of hard to see when we're zoomed out, but if we zoom in, we can see the repeat track numbers labeling the start of every RGT. So for example, here is repeat track 965 in cycles 1 and 2. They're not on top of each other. We have to hunt around a little bit to find those labels on the cycle 3 and greater plot, but we can guess that 962 is one of these. I'm going to use the back button to zoom back out. You'll notice that some of these are labeled on the right and some of these are labeled on the left. That's because we have a mix of ascending and descending tracks. So if the start of the track where I've put the label is on the left, this is the north, that means that it's a descending track. If it's labeled on the right, then it's coming from the south and it's an ascending track. We've read in every 20th data point here so that this is a manageable data set to handle. So when we start zooming in on these, we'll have to reread the data. Now let's take a look at a map view picture of the elevations. So we'll use the scatter plot function for that. And again, we're plotting on top of the mosaic of Antarctica. And I'm filtering these now using an ATL6 quality summary. So we don't have all of the points that we might like to have, but there are relatively few signal finding blunders here. So now if we make a map of elevations using this, we can see that we're high. We've got high elevations on the ridges and among the mountains that are around the ice stream itself. Then we go down to low elevations here on the ice shelf. And we lose signal sometimes, we lose lock on the surface sometime in the edges of the glacier where we're flying over shear margins where there are a lot of crevasses. So the data can get a lot messier there. We don't always track the surface as well as we would like to in those areas, especially if it's cloudy. Okay. So now we're going to look at a particular repeat track and we're going to pull up repeat elevations for that track. So we're going to make one dictionary for the left beams and one dictionary for the right beams. We're still looking at track 27 here. And we're going to try and read in the data from cycles 3, 4, 5, 6, and 7, which are all the cycles from which we might have repeat track measurements. And we're going to plot the data up all on the same axes. So we get sort of a familiar looking elevation profile, but now we have data from 3 cycles, which were the 3 cycles where it was not so cloudy that we missed the surface. We can zoom in on this, and we can see that we have 3 sets of repeat measurements that don't exactly lie on top of each other. We have left and right beams here, so in some cases what we're seeing is a cross-track slope. We're also seeing that cycle 5, as we noticed before, was from a situation where the clouds were pretty marginal. So we may not be seeing the surface very well. And in fact, we're not seeing the surface at all from the weak beam in the pair for cycle 5. So I think we're only seeing the strong beam here. So instead of getting 2 measurements as we would for cycles 3 and cycles 5, so for cycles 3 and cycle 6, we're just getting 1 measurement. Oh, I'm sorry. We're only plotting left beams here. Okay, so we'll get to the 2 beam measurements later on. Anyway, the data don't all lie on top of each other. There's some elevation change. There's some not exact repeating of the measurements here. So there's a variety of interesting stuff that might be happening. Anthony, I said I would give you warning before we would go to the breakout rooms. It snuck up on me. But now I think I've given you a number of tools that let you look at the ICESat-2 data. And so what I'm asking is for people to go into the breakout rooms and spend a little time poking around the data set. So in cells 2.1.2 and 2.1.3, I gave you the code that you need to look at ATL03 and ATL06 together. And so you can go into those cells and you can use the zoom function, or you can try out different beams. So instead of, I think, 2L, which we read before, you can do 2R or 1, 2, or 3. So you can look at different data within the ATL03 data set. And I would ask you to look for places where ATL03 didn't do a good job of finding the surface, where ATL06 is locked onto something that looks wrong, or where the quality summary filtering strategy didn't work out very well. So look for some problems, look for places where there are crevasses on the surface, and try and find some examples of those and post a screen grab in the questions channel. So I think if we have you know, 1 or 2 screen grabs from each group, from each breakout room, that would be great. The other, you've got some stuff from the breakout rooms. I haven't looked at everything that people have. Let's see what breakout room number 3 came up with. So yeah, this looks like some good stuff. We've got examples where, David, is this an example where we have crevasses? Do you feel like the repeat tracks are working pretty well here? Or somebody else from breakout room 3 can talk to this?
We got 2 Davids in breakout 3, so I'll let David Hill speak for our group, I guess.
David Hill? The mute button can be hard to find.
There we go. Sorry. No, I was going to let David Sheen speak to this one because that figure that you are showing right now is one that he threw in there.
Yeah, so this was track, of course I didn't jot it down in the notes. This was track, excuse me, sorry, 530. Should have noted that. What we're looking at are these ridges and surface depressions along on the Pine Island shelf here, and we've got 2 cloud-free cycles, which is great, and you can see, and this shelf is moving 4 kilometers a year. It's flowing from the grounding line out towards the ocean, and so some of these features have moved in this time period between these 2 cycles. So yeah, and I threw in a figure with some of the worldview DEMs. It's a little further down that helps provide a little context for what these things look like.
Ah, there we go. Wow, pretty. So it looks like we've also got, these are Gibbs phenomena, right? This is a ringing filter at the edge of the ice shelf.
So this is track 271. Yeah, and I was interested in those features to the right of that flat section is looking a bit artificial.
I think that that's real. I think the ice actually does that. Yeah.
Wow. Okay.
I don't know why it does that.
It's more of those transverse channels on that south ice shelf over there. You can see a couple of them, but this figure is from 2012. So we're looking at, you know, things that haven't even formed when this DEM was made.
Yeah. Okay, and it looks like you found some sea ice as well. So let's get out of this one. Room 1. Let's see what we've got here. Okay, so this is an example. I'm just going to talk over this one. This one, it looks like an example where they found some ATLS6 that wasn't tracking some repeat data, which shows like the surface disappearing entirely out on the ice shelf. And that looks good. Santiago sent this plot and asked for discussion. What we're seeing here is kind of a common problem with ATLO6. When it doesn't get a good lock on the surface from cycle 5, for example, it can come up with a segment slope that's wildly off. And because when we look at these things, we're generally looking at them in kind of extreme vertical exaggeration. Any sort of significant surface slope looks completely terrible and goes way off the plot. So in this case, cycle 5 is just working poorly, and we're getting slopes that are wrong, although in this case, it seems like the elevations maybe are not quite as bad as the slopes. Santiago, is that what you had your eye on?
Yeah, exactly. Thanks, man.
Okay, great. Sorry, I've got some background noise because there's a printer going here. Room 8. Let's see what these look like. Again, there's some examples where the surface finding is going badly, and some examples where it's going really badly, and it looks like the along track difference may have done a slightly better job than, well, I'd say that the quality summary found the few segments that are working okay on the right-hand side here. And those may have all gotten wiped out by the along track differencing strategy. All right. And then have one from Anna, which is showing, I think, again, an example where the surface moved between two repeats. So out on the ice shelf, things move kind of quickly. You may not see the same location in two subsequent cycles. And again, we're getting out onto the sea ice. In one segment, it looks like the ice may have actually retreated. So we're seeing both sea ice and floating ice in the same place. Sorry, there are kids running around downstairs. And then breakout room 5. Again, found some exotic stuff around the margins. And Nick is asking some good questions that Tyler told him how to find whether we're looking at a weak beam or a strong beam. These are good things to get at. I'm going to get back to the tutorial and just sort of give an outline of what else is in this tutorial. I don't think we've got like 2 minutes to cover the rest of this, so I'm not going to try and overdo it here. There's the breakout room. I found one example on track 469 where the repeats are not especially precise. And so if you plot up the elevations there, you can see that, so we're doing this in map view now. If we zoom in on this map view, look at the elevations, at where the repeats were, you can see that there is some off. I guess this isn't like, okay. Okay. Depending on where you zoom in on this, you can find that the repeats are pretty good or not very good. So this is now plotting the elevations in the top plot and the along track and across track coordinates. So now what happens if you just flatten the different repeats of the data onto the same track? The y-ATC gives you where the track is relative to the repeat ground track. And you can see in this case, the cycle 5 was not even pointing at the same place as cycles 3 and 5. So that's another reason not to love cycle 5 on this. And so I show going farther down that this leads to some apparent elevation differences in the data. And so in the next cell, I show how to correct for this using the across-track slope, which is kind of like a quick and dirty version of ATL11. ATL11 will do this using a polynomial surface. This just uses the across-track slope from one of the repeats to correct for the other repeats. And then in the last cell, I pull in a sneak peek at an ATL11 file and show that it maybe works a little bit better in ATL11 than it does using the simple strategy of just using the across-track slope. So I'm not going to try and take us beyond the time that we have allocated for this, but those are the things that I wanted to cover. I wanted to get people to look at the data and give people some tools for just exploring a set of data that they've downloaded into a directory. And I'll be happy to take any more questions that you folks have. I'll stay on and I can answer questions going further.